Welcome you all, welcome to my next lecture. Now in my last lecture I talked about what is called statement of Green's theorem for multiply connected domain, and now today my plan is to talk about again just I will recall the statement of Green's theorem for multiply connected domain, and then I will talk about some examples and couple of applications of this Green's theorem, and that will most of I think cover the Green's theorem in this course. So my plan is to talk about Green's theorem, once again recall the statement of Green's theorem for multiply connected domain along with some examples and couple of applications. So that's for today's plan of the lectures. Yeah, so as I said, I recall the what is called statement of Green's theorem for multiply connected domain of region that I have of course explained in my last lecture, but just recall with once again. So that's the kind of title, Green's theorem for multiply connected region. Now what is the statement? Statement is the following. So again I am actually restrict myself in two-dimensional Euclidean space. So if I have a R2 and suppose if I have a say simple closed piecewise smooth curve in R2, so that I denote it as C, the bigger one, the curve, this is the one curve. So C simple closed positively oriented piecewise smooth curve, and let Ck the finitely many again simple closed positively oriented smooth curve, but that lies to the interior domain bounded by my what is called enclosed by contour C. So that's I have written. So Ck denotes the finite number of simple closed piecewise smooth curves, all are positively oriented and that are interior to C and whose interior points have no points in common. So that means these are actually disjoint. So I have a big curve C, simple closed curve, then I am taking interior of C finitely many C1, C2, Cn, these are disjoint. So these are, if this is the case, then what is my domain? I am considering the domain which is nothing but the interior or interior domain, interior bounded domain by enclosing the simple positively oriented piecewise smooth contour C. But I am going to subtract something from that domain. So what is that? So that means each C1, C2, Ck, that's also simple closed what is called curve in interior to C. So they also kind of have a interior bounded domain. What you do, you consider the domain D bounded by your simple closed contour C and then take out the portions of the domain bounded by each Cis which are interior to C. So therefore what we will have at the end of the day, so this is actually the green one, this is the domain. I mean you have a domain but there are some holes because you see the white part it's not here, which is nothing but the interior domain bounded by C1, C2 and Cn. So that means you have a domain but there are some holes. This is called multiply connected domain. Once I have that one, so that's exactly I have written blue color region. And if I start with a very nice vector field capital F which is continuously differentiable vector field defined on an open set S which contain my domain D, which I just explained what is my domain, then what is the statement of Green's theorem? It says that you consider the vector line integral of your vector field capital F over C, and then what you have to do, you just again sum it up all the vector line integral of capital F over Cis, that C1, C2, Ck, these are interior to C. You have to sum it up and then what you have to do, you have to just take subtract. You have to subtract this the vector line integral over each Cis, that means C1, C2, Cn, which lies interior to C. You sum it up and you just subtract these portions from the vector line integral of capital F over C. And what it turns out that if I subtract that one, then it can be written as a double integral over the region D of this object, what is called del n del x minus del m del y, where my capital F is the vector field whose first component is capital M, second component is capital N. So that can be written as a double integral, and which again this one is very easy to see. If I look at my vector field in R3, then you can calculate the curl of F dot product with k cap, that means 0, 0, 1 vector, then it turns out that this is exactly equal to this one. So that's the statement for multiply connected domain, the Green's theorem. So therefore the vector line integral of the bigger curve over of capital F, and then you subtract the interior one, you calculate the vector line integral. If I subtract that object from the vector line integral over the big kind of curve C, contour integral over C, then that difference can be written as a double integral over the multiply connected domain D, for integrand is del n del x minus del m del y. So that's the statement for multiply connected region. Now let's see what is the consequences. Okay, so now I am going to give an idea how to prove the Green's theorem for multiply connected region or domain using the Green's theorem or using the statement of the Green's theorem for simply connected region or domain. So, that is it. So, what you do, dividing the multiply connected domain into two simply connected domains or region, and simply connected domain you know the statement of Green's theorem. So, therefore, you have the final conclusions. So, look, so what I said, so suppose this is a multiply connected domain. So, this is, that means I have a domain D which is the interior to this curve C, and there is a hole. So, this is not part of the domain. So, then my domain is this one. This is a multiply connected domain. This is also a multiply connected domain. So, the red one, okay. What is that? So, because this is also a domain, but there are two holes are there. So, this is the one hole and this is one hole. So, therefore, this is a multiply connected domain. Now, if I have a multiply connected domain, suppose the first one contains only one hole and second one contains two holes. So, that means the bigger curve is C and the smaller one, that C1 C2 which is interior to C, and the domain enclosed by C1 and C2, this is not part of my domain. So, there my domain is like that with two holes. So, this is a multiply connected domain. Now, the question is how I can apply what is called the statement of Green's theorem to have the statement of the multiply connected domain. So, look what I said. It says that by introducing straight line curves, we can convert the multiply connected domain into two simply connected domains, and then we apply Green's theorem for simply connected domains to them. Now, how to do that? Now, look first here. So, suppose you come back this picture. So, I have a domain which has a hole, right? Now, how to make it to a what is called break up into two parts and make it a simply. So, what do you do? So, like for example, I introduce a line, for example, or this small one is there. So, suppose this is one line and this is another line. So, this is one line. So, what I will do? So, now this is my domain. So, this is the gray one is the domain, or this white one is not a part of the domain because it is a multiply connected domain. Then what I will do? So, suppose I want to break this multiply connected domain into two parts. So, what I will do, you see, look. So, if I draw a straight line like this one and this one, so now I can break up into two parts. Why? Because look, so this is the what is called the curve in the outside. So, suppose this is my curve. So, I will go in these directions, and then once I reach here, then I will take these directions, okay, and then I will move in these directions, okay, and then I will go and I will. So, that means, so first if I have two straight lines, one is this one and another this one. So, first I will have this region, this is one of the region, another one I will show. So, maybe I will start from here, I will go here, I will go in these directions, I will go and then I will come back. Okay. So, therefore, somehow I can break up my domains into two parts, in this one and the right one. So, therefore, first domain maybe I can think about. So, this if I talk about this one, so that means the first one I am talking about, this is the one, okay. So, this is the one, maybe you can put some directions, okay, and another one is that this same, this is the one, okay, then I will have this. So, therefore, now this is very nice, like this is not part of the domain. So, therefore, if I consider this curve, simple closed contour, this is the curve, right. So, this interior bounded domain, it is part of the domain. So, therefore, this is a simply connected domain. So, this is simply connected. Similarly, if I have this simple closed contour and the interior region bounded by that, this is, so this is one domain D1, this is one domain D2, and this is the corresponding simple closed curve. So, like first one is that if I go in these directions, so this is the one simple, and second one is that this is the one. So, now I can break up my multiply connected domain into two parts, both of them are simply connected. So, that means that domain once I have, because already I have domain, this portion is not there now. So, therefore, if I can break up, so this is not there. So, I can break up into two parts D1 and D2, and both of them are simply connected, and I know the statement of Green's theorem for simply connected domain. So, you just write the statement for D1 and D2, and then you just take the union, and it will give you the what is called the statement of multiply connected domain for the multiply connected domains, the statement of the Green's theorem. So, that exactly I have written. So, by introducing the straight line curves, we can convert the multiply connected domain into two simply connected domains, then we can apply the Green's theorem for the simply connected domain. So, this is for one hole, and what will happen for domain for two holes. So, again the same thing, you see I have already done. So, what I will do, I can break up into two parts. So, for example, consider this simple closed contour C. So, I can say this is C1 or C2, what or some C2idel. What is that? So, I will say maybe I can start from here, okay, or maybe I can start from here. So, I will go in these directions, okay, I am coming. So, this is one straight line, this is another straight line, this is another straight line, three straight lines I have introduced. So, therefore, if I reach here, then I will go in these directions, then I will come back this direction, and then I will go in these directions, and then I will go in this direction, and then this one. So, this is one of the simple closed contour whose interior region bounded by this one. This is simply connected. Another one, what? Maybe I can start from here, or maybe I can start from, say, I am going in this direction, in these directions. Once I reach here, I will come back in this direction, then I will go move in this direction, then I will come back here, and then I will come back here, then I will go in this direction, and then I will reach. So, therefore, one part is this one, another part is this one. So, therefore, I can break my multiply connected domain into two parts by introducing straight lines. So, this is one, this is one, this is three straight lines, and therefore, I can break up into two simply connected domain, and in simply connected domain I know the statement of what is called Green's theorem, and if I just patch it up or take the union, then it will give you the statement of what is called Green's theorem for multiply connected domain. So, that is the idea. Is the idea I am talking about. I am not talking about the details of it, but anyway, so if you just use this the kind of idea, and if you do that, then you will be able to have this statement. That means the vector line integral over C, and if I take out the, if I subtract the vector line integral over Ck's which are sitting interior to C, then this difference can be written in terms of the double integral, and which is nothing but in terms of curl of the vector field dot k cap, or if I look my vector field capital F in R3. Okay, so I hope so. This is the kind of statement and little idea of the proof using simply connected domain. Now, let us discuss some examples, then it will be more clear. Okay, so before that, one applications I have given, applications of Green's theorem for multiply connected region. So, the statement of multiply connected domain, it is given. I can think about it's like deformation of contour. I'll explain what do I mean by deformation of contour. Look, so this I have written as a statement. So, look, so let capital F, which first component is capital M and second component is capital N, be a C1 vector field, that means continuously differentiable vector field on an open set S in R2. Let C1 and C2 be two simple closed piecewise oriented smooth curve in S such that C2 lies interior to C1. So, that means what? If I draw a picture, so therefore, this is, suppose this is my C1 and C2 lies interior, so therefore, this is my C2. Okay. So, both of them is same oriented, positively oriented or counterclockwise oriented, and both of them C1, C2 are simple closed piecewise smooth curve in my domain S. Suppose this is my domain S, okay, of my vector field capital F. So, I have a C1, I have a C2, two simple closed piecewise smooth curves. C2 is lies interior to C, or C2 lies inside to C1, such that the region R between C1 C2 is contained in A. So, what is the region between C1 and C2? So, this is the region, right. So, this is the annulus. That annulus of course is S is the bigger one, this is the one. So, therefore, this is the R, and which is sitting inside S, okay, contained in S. Now, if C1 C2 have the same orientation, you see C1 is anticlockwise, C2 is also anticlockwise, same orientation, does not matter, it should be anticlockwise, it should be clockwise as well, but both of them should be clockwise or both of them should be anticlockwise. And if suppose the vector field curl is 0. Now, if you remember when I talked about the notions of what is called divergence, curl and gradient, that time I said that if the curl of my vector field F is 0, then this vector field it is called irrotational vector field. So, therefore, if I start with a vector field which is irrotational, that means curl of F is 0 in my region R, which is nothing but the annular region bounded by C1 and C2, then it says that the integrations vector line integral of capital F over C1 minus vector line integral of capital F over C2, it is exactly equal to the double integral of this object curl of F dot k cap, but curl of F is 0. So, therefore, this is exactly equal to 0. So, what it gives actually the integration vector line integral of capital F over C1 is exactly equal to vector line integral of F over C2. Okay. So, now look why this is 0, this is very nice, because you see, so this is like multiply connected region, that the region R I have multiply connected region because the outer. So, this is C1 is the simple closed contour, right. So, therefore, consider the region bounded by C1. Then C2 is another simple closed positively oriented contour sitting inside C1. So, therefore, the region here bounded by this one. So, what region I am considering? I am considering the region, you see that I have written, I am considering the region between C1 and C2. That means, I am considering these portions. So, that means it is there is a hole in that region R. So, therefore, it is actually multiply connected region. So, therefore, I am considering the interior region bounded by C1, and then I subtract the interior region bounded by C2. So, that means the region R is multiply connected. Now, if I apply Green's theorem, I know the statement of Green's theorem, right. What is the Green's theorem says? So, if I have a multiply connected domain and this is the kind of simple closed curve C1 and C2 is sitting inside. So therefore there is only one hole. So therefore what it says, integration over C1 f dr minus integration over C2 f dr. So that means only one simple closed contour sitting inside C1, and that I can write in terms of the double integral over R. And what is my object? This should be del n del x minus del n del y, right? Del n del x minus del m del y times dA, and that can be written as double integral over R curl of f dot k cap, right? That's the exact statement. You see, look at the statement. You see, this is the vector line integral over the bigger simple closed contour whose interior contains small c1, c2, cn. That means you have to subtract. Now here what is the bigger one? My bigger one is the c1. This is the bigger closed simple closed contour whose interior contains my simple closed contour c2. So therefore integration over c1 minus integration over c2, that exactly equal to double integral over R curl of f times k cap, right? That's correct. But I started with my vector field is irrotational, so that means curl of f is 0. So therefore this integrand is 0. So therefore it will give you 0. And what it implies is that integration over c1 is exactly integration over c2 if my capital F is irrotational, that means curl of f is 0, and c1 c2 have the same orientations. So if that is the case, then it says that kind of, so that means I have two contour, right? Simple closed positively oriented contour c1 and c2. So therefore somehow the vector line integral of capital F over c1, it's same as vector line integral of capital F over c2. That means I can deform it from c1 to c2. That you can think about as a deformation of contour. Okay, but this should be true provided your vector field should be rotational and c1 c2 have the same orientation. That is a very simple applications of my Green's theorem for multiply connected region, because this region is very nice. You have only one simple hole. Okay, so therefore, so this left hand side only integration over c1 minus integration of c2, and right hand side should be curl of f dot k cap. This is the integrand, and you have to have the corresponding vector what is called double integral. Okay, I think this dA is missing. Maybe you can write dA. Okay, there it should be a dA. Okay, double integral. Okay, so double integral of the integrand curl of f dot k cap, and which is nothing but actually del n del x minus del m del y times dA. Double integral. But f is capital F is irrotational, that means curl of f is 0. So therefore this is 0. So therefore integration over c1 is exactly equal to integration over c2 of my vector field capital F. Okay, so this is one of the nice applications of Green's theorem for multiply connected region. Okay, so that means if I have a domain which has only one hole which is multiply connected, that means integration over c1, the bigger simple closed contour, the vector line integral which is same as the vector line integral with the smaller simple closed contour which is sitting interior to C. Okay, interior to C1. Yes. Okay, so now let's just look at some examples, then it will be more clear. Okay, so what is, I think this kind of things I already discussed. This is called non-conservative field, or but it is irrotational. Okay, so non-conservative means what? If you remember that there is definitions of conservative vector field. So if I have a vector field, suppose in some domain S subset of R2, then it is called conservative if I take any simple closed piecewise smooth curve inside my domain S, then the corresponding vector line integral over this. So suppose this is my S, okay, and suppose I have a vector field. So suppose this is R2, right? So if I say vector field from A subset of R2 to R2, and it says that capital F is conservative. This is called conservative if I just recall the definition. So that means it's whatever simple closed positively oriented contour I can take, simple closed positively oriented smooth contour if I take C, then the vector line integral of capital F over this contour should be 0. That is called conservative if this is the case. That means whatever simple closed, what is called smooth positively oriented or some orientation contour if I take, then the corresponding vector line integral of capital F over this contour it should be 0. And it is not conservative means what? I can have the example of one simple closed smooth contour which is sitting inside S, but the corresponding vector line integral should be non-zero. And that you see, so that kind of example I have already discussed. Suppose if you consider this kind of field capital F, which is actually irrotational vector field. Irrotational vector field means what? That means curl of F should be 0. Right? If I calculate the curl of F, so that means looking at what is called in 3 dimension. So you can, what is the first component? This should be minus y by x square plus y square. Second component is x by x square plus y square. Third component is 0. If I calculate the curl of F, it should be 0. So therefore it is irrotational vector field, but it is not conservative. Why? Because if I consider this nice this is a circle, right? This is simple, smooth, positively oriented contour sitting inside my domain. What is my domain? This is my domain R2 minus 0. That means whole R2 except the origin. So that means a punctured what is called two-dimensional plane. And if I consider circle with centered, what is the center unit radius? Okay, this is a 1 radius, and this is a circle positively oriented smooth curve. Then if I calculate this vector line integral over C of my vector field capital F, and if you calculate it, it turns out that it is exactly equal to 2 pi, and which is a non-zero quantity. So therefore F is not a conservative vector field in this term. But if I consider the what is called curl of F, this is actually 0. You can, if I calculate it, curl of F, okay. So if I calculate it, this curl of F has to be 0. That means it is actually irrotational vector field. Okay, so again I just repeat. So what is that? So it should go on actually. So therefore if I have, this is my origin, this is my circle with centered 1, okay. So now look, so since it is a circle of radius 1, so therefore it will have a parameterizations, you know. So this is cosine t comma sin t, t running from 0 to 2 pi. What is the derivative? Minus sin t comma cosine t. Now you calculate the vector line integral capital F dr. So what is the definition? You know, if I just recall the definitions of vector line integral, since I have a parameterizations of my curve C is RT, so this is nothing but f of RT, then r prime t dt, t runs from 0 to 2 pi, and this is a dot product f of RT. You know what is f of RT? A capital F is given. F of RT, if I do it, so RT is cosine t, comma, so what is my capital F of xy? If I just break up into this one, minus y divided by x square plus y square, and then x divided by x square plus y square, right? If I consider F of RT, then what will happen? The denominator will give you 1 cos square t plus sin square t, right? So what will remain is that minus cosine minus y, no? So therefore minus sin t and then cosine t, and that exactly this one, minus sin t comma cosine t. R prime t, this is the 1. Take the dot product. So okay, this is the dot product, that means the corresponding inner product. That means this is sin square t plus cosine square t, this is dt, and this is non-zero. So therefore this vector field capital F, it is actually non-conservative vector field, because I have a simple closed positively oriented smooth contour, and if I consider the vector line integral, which the value is exactly 2 pi, which is non-zero, therefore it is not conservative, but it is irrotational. That means if I consider this vector field inside R3, that means whose first component is minus y by x square plus y square, second in x by x square plus y square, third component is 0, and if I consider the curl of this vector field, you just calculate it, it will give you the 0. So therefore it is actually irrotational, okay, that I already discussed. So now what it says is that, now see, this is very nice. It says that if I consider the same vector field, actually this is irrotational but not conservative on this domain D star, which is the punctured plane. Now look, if I said let C be any simple piecewise smooth curve in D star which encloses the origin, then I am saying that okay, calculate what is the vector line integral of capital F over that C. How do you do that? See, I didn't mention anything about the parameterizations of C. I just say that take a simple closed piecewise smooth curve in D star. So what is my D star? This is my R2 minus 0, that means there is a hole, 0 0 is not there, and I am considering any arbitrary, or there should not be any figure 8 kind of things, so therefore I can write it. So what I am trying to say is the following. So this is my domain, there is a hole here because origin is not here. Suppose I am considering this kind of simple closed contour C, and I want that okay, calculate C f dr. But you see, if I consider C, which is a simple closed piecewise smooth, that because arbitrary simple closed piecewise smooth curve in this star like this one, it's very difficult to have the parameterizations. Like for example, if I have a circle, if I have a square, if I have a rectangle, then you can have easily the parameterizations. But if I choose a arbitrary simple closed piecewise smooth curve, there could be many, right, infinitely many. But point is that the getting a parameterization is very difficult. Now if I do not know the parameterizations, then how can I calculate the what is called vector line integral of capital F? So therefore how can I handle those kind of problems? But I just give a statement of a what is called Green's theorem for multiply connected domain, and as an application, if you remember that if I have a simple closed contour C, and if the interior of C contains another simple closed contour piecewise smooth, same orientations, then the vector line integral of capital F over C1 is same as vector line integral over C2. Like deformation, I know, I will use that fact. You see, look. So therefore this is my what is called simple closed contour positively oriented. This is my C, that I do not know any parameterizations. However, if I take a small circle around the origin, say with center A, and let it be denoted as CA with the same orientation, anti-clockwise the same orientation with C. But I know the parameterization of CA because it is a circle, right? So that's, you see, that's exactly I have written. Let C of A, which is nothing but a circle of radius A centered origin, where A is positive, is a fixed constant be such that CA lies inside the curve. Now that I can do that, na? Because whatever simple close positively oriented or some orientations a piecewise smooth curve, if I take enclose my origin, I can have always a small circles of radius, some radius A. So this is my C. Now you can choose this circle. For example, if I take another, so it says, so whatever, so like this this simple close piecewise smooth curve enclosing the origin, there also I can take a very small circle of centered 0 radius A, that I can always have it. So therefore, if I take this, that is always possible. Whatever simple close piecewise smooth curve, if I take in this star encloses the origin, that will always contain a circle of centered 0 radius, whatever small, what that will have a positive, and that circle sitting inside the interior of C. That's the kind of conclusions. Okay, so that's what exactly I have written. Let CA, where A is positive, is a fixed constant such that the curve CA, which is nothing but a circle of centered 0 radius A, which is lies inside the curve C, and that is always possible. Note that curl of F is 0. So that in my last slide I just said this is a irrotational vector field, therefore curl of F is 0. So therefore, by applications of Green's theorem for multiply connected domain, so therefore integration over C minus integration over CA. So that means the domain I am considering bounded by C and CA, that means this is the domain I am considering which is multiply connected, and as an applications of my Green's theorem says that vector line integral over C is same as vector line integral over CA. If you remember, that's exactly the application. Na? This is the integration over C and exactly equal to integration over C2, right? This is because this is my C1, this is my C2. So this is a one hole is there, this is multiply connected region, right? Same thing. So therefore, integration over C, which will be minus integration over CA, then by statement of Green's theorem in the multiply connected domain, this is nothing but curl of F dot product with K cap with this what is called double integral. But since this my vector field capital F, which is irrotational, therefore this is 0. So therefore, what it turns out is that the vector line integral of capital F over C, which is same as vector line integral over capital F over CA, and that you can calculate it. Why? Because I know the parameterizations of CA and I know my vector field capital F, and what is the value that I just exactly calculated in my last slides. Look, this is my circle of centered 1 and radius 1, centered 0 and radius 1. So this is circle of centered 0 radius 1, and what is the corresponding vector line integral? This is actually 2 pi. So the same thing. So if I consider a circle of centered 0 radius A, so it doesn't matter which radius I am talking about, it could be anything, either 1, 2, whatever it is. So whatever circle you can take with centered origin radius A, this vector line integral you can easily calculate, because I know the parameterizations of CA, and that I have done in my last slide. If you do that, then it will say that this vector line integral is nothing but 2 pi, and therefore the corresponding vector line integral of capital F over an arbitrary simple closed piecewise smooth curve, that I do not know anything about the parameterizations, but that I can calculate, and that value is 2 pi using Green's theorem for multiply connected domain. That is very nice applications of what is called Green's theorem for multiply connected domain. So even if I tell you that okay, calculate the vector what is called line integral of your vector field capital F over an any simple closed piecewise smooth curve inside this star, and you do not know the any kind of parameterizations of that one, but you can easily calculate it. What you do, you just take a very small circle around the origin, that is possible, which lies interior to C, that is also possible, and you once you have a circle, you know the parameterizations, and by Green's theorem for multiply connected domain, it says that integral over C, that C is have no idea about the parameterizations, but it is a simple closed piecewise smooth curve enclose your origin. This is exactly same as vector line integral over a small circle of some radius with centered origin and radius A, and that you can easily calculate because you know the parameterization of CA, and therefore in this way you can calculate the vector line integral of capital F over any simple closed piecewise smooth curve in this star enclosing the origin. This is very nice. Okay, so I think this is clear. Now this is another example, same vector field I am considering. What I am saying is that same example, but this time actually curve does not encloses the origin. So that means what is my domain here? Domain is R2, except there is a hole. But this time what see, I am considering the same vector field, which is irrotational vector field of this domain. C be any simple piecewise smooth curve in this star which does not encloses the origin. That means you consider these kind of things, na? Or something like that. So, this is your C, whatever it is. Then it follows that integration over C, which is nothing but that. Now, look, see, what is that? This is integration over C, I know. Now, this C is what is the interior region? Interior region is perfectly all right. This is actually simply connected, right? There is no hole inside. So, therefore, this what is called vector line integral capital F over C, and then since my domain is simply connected, this is the corresponding R region. So, therefore, what is this? By the theorem for Green's theorem, statement of Green's theorem for simply connected domain, what it says? This is nothing but the double integral over R curl of F dot k cap, but curl of F is 0. So, therefore, this is always 0. Okay. So, and therefore, R is the enclosed region by C. Okay. So, therefore, the only problem you will face if I take a simple closed piecewise smooth curve in this star enclosing the origin, there it will give the vector line integral is non-zero. But if I take any simple closed piecewise smooth curve in this star which do not contain, you see, which does not enclose the origin, then it will be like this kind of simple closed curve, piecewise smooth curve, and then if I take the region interior bounded region bounded by C, then it is a very nice domain. It is actually simply connected, right? Now, once I have a simply connected domain, then what is the corresponding statement? Vector line integral of capital F over C, which is nothing but the double integral over R curl of F times dot k cap. What is my R? R actually you can think about either interior domain, so the interior domain D along with the boundary, or you can think about this is the R. It does not matter whether double integral over R or double integral over D I am considering, but this is the corresponding statement for Green's theorem for simply connected domain. So, in vector line integral of capital F over C, which is same as the corresponding double integral whose integrand is curl of F dot k cap, but since my capital F is a irrotational vector field, so therefore curl of F is 0, so therefore this is actually 0. So, therefore, if I take any simple closed piecewise smooth curve in this star which does not encloses my origin, the value of the vector line integral of capital F is 0. But if I consider what is called simple closed piecewise smooth curve in this star, that means R2 minus 0, which encloses my origin, the value of the vector line integral actually equal to 2 pi. So, this is very nice. Okay. So, I think so that is like kind of statement of Green's theorem for vector line integral, Green's theorem for simply connected domain as well as multiply connected domain. Couple of examples, couple of applications I have discussed. So, now I am come to the what is called the statement of Green's theorem in the unit normal vector. So, that is why I said vector line integral with unit normal vector, or that is a flux integral in the 2-dimensional things. So, what is that? So, look, so it says that, okay, so just to give a statement of Green's theorem for vectorial form, so I need to recall some couple of concepts. So, what is that? So, let C be a piecewise smooth oriented curve in R2 with my parameterizations xt, yt. Then the directions of the tangent to the curve are RT, which is nothing but R prime t, x prime t, y prime t. Then what is the direction of the normal? So, if I have a curve C, so this is my directions of the tangent. Okay, so so what is the normal? It is perpendicular to this one. So, what is the tangent vector? Tangent vector is R prime t, x prime t, y prime t. That means derivative of x and derivative of y. Then what is the direction of normal? It should be perpendicular to the tangent. So, if I calculate it, it should be minus y prime t, x prime t. Okay, observe that R prime t and dot nt is equal to 0 because tangent is perpendicular to normal. So, that means what is the normal unit normal vector? You have just divide by norm of t. Therefore, n cap I am defining it nt by norm of nt. Now, if my capital F, which is capital M plus capital M comma capital N, is a continuously vector field on a set S containing my curve C, then you know the corresponding scalar line integral of this object f dot n cap ds, which is same as m dx minus n m dy minus n dx. It will change because this time I am actually considering the what is called the vector line integral. I think the scalar line integral of the what is called normal component of f. So, that means there are two components, either tangential component or normal component. If it is a tangential component, that means f dot t should be there. Here I have f dot n cap, where n cap is the unit normal. So, this is the corresponding scalar line integral of the normal component of my vector field capital F. And if I do that one, this exactly equal to integrations over C capital M dy minus capital N dx. The above integral is called the what is called flux integral. I think you cannot see these things. So, the above, if I write it, so this you cannot see, so I you can write it. So, the above integral is called the flux integral of capital F across the curve C. So, that is what it says. That is the kind of physical implications. So, that part I think I have discussed when I talked about scalar line what is called line integral, scalar line integral and vector line integral. There I have discussed. You have two components, tangential component and normal component. So, this is the normal component. So, this what is called scalar line integral of this functions f dot n cap, which is exactly equal to m dy minus n dx over my what is called curve C, which is sitting inside my S if capital F is a C1 vector field. Once I have that one, the above integral, of course this is known as the above integral, is called the what is called flux integral of F across the curve C. Okay. Once I have that one, then look, this is the statement of Green's theorem. You see, I have the normal form of written. That means I am dealing with the normal vector instead of tangent vector for a simply connected region. What is that? So it says that this is the Green's theorem, it's a statement normal divergence of flux form. So let capital F, which is capital M comma capital N, be a continuously differentiable vector field on an open set S in R2. Let C be a positively oriented piecewise smooth simple closed curve in S such that the interior bounded domain D enclosed by C, which lies entirely inside C, exactly same for the simply connected region, the earlier statement. Now if you just take your R, which is nothing but the interior domain bounded by C along with the curve C, and this is also in IS. So therefore this region is simply connected. Now it says that the corresponding line integral or vector line integral, I should say that this is a scalar line integral of this object f dot n cap. That means the normal component of f you take, then you consider the corresponding line integral over C, and which is nothing but the flux, which is same as integration over C m dy minus n dx, and that is exactly equal to the double integral over the region R of this object del m del x plus del n del y, and this is nothing but the divergence of capital F. If I calculate the divergence of capital F by looking at in R3, then it is exactly boils down to this one. So this is the picture I have given. Okay. So this is my domain S. So this is simple closed positively oriented curve C, which is the interior region E1 D. R is nothing but D union C. Then the corresponding flux, which is nothing but the what is called scalar line integral of this object f dot n cap ds over C, which is nothing but m dy minus n dx, and this is exactly equal to the double integral, and which is nothing but the divergence. So this is actually the statement of Green's theorem, but normal form. You see, but when I talked about the Green's theorem, the tangential form, there we will have f dot t, if you remember. I think if I go back very long, I think it will see that, I think that what I have written, right? Yeah, you see f dot ts is a tangential component. Okay. So this is the corresponding scalar line integral I have talked about. Now this is the statement for vector line integral. That means instead of tangential vector, I am considering the normal vector. Okay. And this is actually called the flux that I have seen. So the integral, actually this is the integral, it says that it is the flux of this vector field around the curve C. Okay, so this is, I think, last part of this one. So the interpretations of Green's theorem, that means the flux form, that means the vectorial form, that means this is the form. The Green's theorem for normal or divergence or flux form, whatever you can say. Normal stands for this actually normal vector. Divergence means I can write this scalar line integral as a divergence of this double integral, and this is nothing but the flux of my vector field capital F around the curve C, that is the flux. Okay, so if I just see the interpretations of this one, it says that let capital F denote the velocity of a fluid moving in the plane and assume unit density, then the divergence of capital F of my vector field at x measures how the fluid is moving from the point x. So this is the interpretations. Now integrating this over, so divergence, what I am doing, I am integrating divergence over the region R. So that's what it says, that integrating this over the whole region R, we obtain the net change in the amount of fluid in the region R, and there is another way to measure the same quantity. What is that? Merely stand by the boundary of R and see how much enters and leaves. So there are two things. Either I am talking about in terms of the interpretation in terms of the double integral over the region R, or I can talk about or the same object over the kind of line integral over my contour C. So therefore it says that the above idea can be stated closely or loosely, I should say, the above idea can be stated loosely as follows for the better understanding. What is that? It says that let capital R denote a room, okay, in which a party is taking place. Fine, perfectly all right. Capital F of x is the velocity of a person standing at x. So x is fine, standing, the person is standing, and capital F at x is nothing but the velocity of that person. Then look, then one can measure the change in the number of people at the party either by one, what is that one? The counting the people inside the room in the room R, or number 2 is that standing at the doors, that means which is nothing but the boundary of the region, that means this is del of R, and counting how many people enter and leave. So that means you can interpret 2 ways, either inside the room what is going on, or look at the boundary what is going on. Inside the room means you just, that means the way, that means I am talking about the double integral, that means you count the number of people inside your room, or what you do, you stay in the boundary, that means which is nothing but the contour C, and then look how many people are coming and going. So that's exactly the standing at the doors and counting how many people are enter and leave. So the number 1 is the right hand side, because number 1, that means I am talking about the total number of people, that means actually the interpretation is that I want to calculate the double integral over the region R. That's what I have written. The number 1 is the right hand side quantity of flux form of Green's theorem, that means the double integral. And what about the left hand side 2? That means I am standing at the boundary of the region, that means I am talking about the line integral. That means the 2 is the left hand side of the quantity, that means this is the left hand side of the quantity, that means over the boundary I am talking about, and this is the right hand side, that means in the region R. The region R enclosed by my what is called simple closed positively oriented smooth contour C. So that means that's the way you can interpret. Okay. So that exactly I have written. So if R denotes the room in which party is taking place, and capital F at X is the velocity of a person standing at X, then one can measure the change in the number of people at the party either by number 1 counting the people inside the room, or number 2 standing at the doors, which is nothing but the boundary, which is del of R, which is nothing but C, counting how many people sleep or enter. So therefore the number 1 is actually the right hand side, that means the double integral, and the number 2 is the left hand side, that means the what is called line integral. Okay. So I think that's all what is called for Green's theorem. So in the Green's theorem I have introduced, like, of course I recall the notions of contour, okay, and then I give the or some region, of course I recall the notions of what is called domain, simply connected, multiply connected. Then we have kind of statement of Green's theorem for simply connected domain, and then we have a statement of Green's theorem for multiply connected domain. And of course in the simply connected we have 2 types of statement. One is the tangential form of my vector field, another is the normal form, that now today actually I have discussed. Couple of examples I have discussed, couple of applications of Green's theorem I have discussed. So I think that's very brief about Green's theorem. So here I will stop about the Green's theorem discussions. In my next lecture I will start. Now I have only 2 concepts left. One is the divergence theorem and another is the Stokes theorem. Now in the Stokes theorem and divergence theorem, you see I need to recall once again the concept of surfaces. Once I recall the concept of surfaces, then surface integral I have discussed, and once I have the notions of surface integral, then I can state the notions of what is called divergence theorem and Stokes theorem, and then there also I will talk about little bit of examples and applications of Stokes theorem. So I think I should stop here. So this ends the discussion about Green's theorem. In my next lecture I will start the discussions on Stokes theorem and divergence theorem. Thank you.